Hello guys, welcome back to my channel Gamma Di Gamma. So in this video I would just like to do a little less serious topic. Laplace transform of hyperbolic trigonometric functions. So let's get started. Okay, so before we start, this is a small recap. The Laplace transform of f of t is defined as integral from 0 to infinity e raised to negative st f of t dt, and this will be a different function but of s. Okay, so let's start with Cosh. The Laplace transform of Cosh of at, where a can be just an arbitrary number. So I just write the definition. Now Cosh is nothing but 1/2 e raised to at plus e raised to negative at dt. We can split these guys up by their linearity. So we have 1/2 integral from 0 to infinity e raised to negative t s minus a dt plus 1/2 integral from 0 to infinity e raised to negative t s plus a dt. I'm just using basic properties of exponents. So this thing becomes 1/2 times, well, s minus a. If you evaluate the exponential from 0 to infinity, you just get a 1 plus 1/2 1 over s plus a. If you don't believe me, you can do it on a piece of paper, it's fine. So we have 1/2 cross multiplying this thing, 2s over s squared minus a squared, which is equal to s over s squared minus a squared. That's the Laplace transform of Cosh of at. Now for the Laplace transform of Sinh at, we again use the definition. Sinh is 1/2 e raised to at minus e raised to negative at dt, and by linearity we end up with similar antiderivatives after evaluation but with a negative sign. So 1/2 1 over s minus a minus 1/2 1 over s plus a. So if we just evaluate everything, we are left with a over s squared minus a squared. That's the Laplace transform of Sinh of at. So we have Laplace transform for the Cosh and the Sinh. Time to move on to their multiplicative inverses. In other words, the Sech and the Csch. Okay, so we have Laplace transform of hyperbolic secant of at. So we just write the integral definition and then the definition of the hyperbolic secant. So we have 2 over e raised to at plus e raised to negative at dt. Now what we can actually do is have the 2 over here integral 0 to infinity e raised to negative st have negative powers everywhere, so we divide by e raised to at in the numerator and denominator, so we get a negative power on top, and in the denominator we have 1 plus e raised to negative 2 at dt. Now let's implement the substitution. U equals e raised to negative t, so du is negative e raised to negative t dt, and that just makes everything a little more interesting because now we have a 1 and a 0 here. This thing becomes u to the s plus a because of the power rule divided by 1 plus u raised to 2a, and dt is just negative du over u. So that negative will be used to flip this upper and lower bounds. We have a negative 1 because of that du. Well, now we can actually use the geometric series to basically convert the denominator into something a little more practical, because recall the sum from n equals 0 to infinity of a times r raised to n was just a over 1 minus r, assuming that magnitude of r was less than 1, and that's certainly the case here because u is between 0 and 1, so that criterion is already satisfied. So 2 times sum from k equals 0 to infinity, plus is a minus and a minus, so we have minus u raised to the kth power, so we can take the minus 1 to the k outside, integral 0 to 1 u raised to s plus a minus 1 times u raised to 2a times k du. Now we can evaluate this antiderivative. This will just become u raised to s plus a plus 2ak over s plus a plus 2ak from 0 to 1, so that automatically becomes minus 1 to the k over s plus a plus 2ak. Now I would like to divide by 2a everywhere, so I have 1 over a, sum from k equals 0 to infinity minus 1 to the k, so we just get a k plus s over 2a plus 1/2. Now there is something important that I would like to discuss. Recall that if we wanted to define the Hurwitz zeta, for example, of, I don't know, s n, that would be sum from k equals 0 to infinity of, let's see, 1 over k plus n raised to the s power. But now we are just sort of generalizing this process in what's called the Lerch transcendent. And generalizing in what way actually? Generalizing in this way. See, assuming we have defined phi of z s alpha as sum n equals 0 to infinity 0 to the n divided by n plus alpha to the s. So you see, generalized in such a way that now we have this argument on top, this z to the n, such that when z is 1, you get the Hurwitz-Zeta function again. So it's actually a chain of generalizing stuff. The Hurwitz-Zeta was a generalization of the Riemann-Zeta, because we have this other term apart from the summing index in the denominator, and we even generalized beyond that and introduced this extra argument on top. And we are exactly going to use this for this guy, because notice that in our case z was the thing on top is -1, s, which is the power, is 1, alpha, which is the thing apart from the summing index, is s over 2a plus 1/2. So we finally get, using this Lerch transcendent definition, 1 over a Lerch transcendent, or phi of -1 s over 2a plus 1/2. And I think that's all I can do right now. You might find more detailed research papers which have gone beyond this definition and probably done something crazy, but I'm gonna put it like this. So let's move on. Okay, so moving on to the Laplace transform of the hyperbolic cosecant of AT. All I've done is just written the definition, expanded using the definition of the hyperbolic cosecant, and we can repeat the process like before, dividing by e raised to at to get negative powers everywhere. So we have 1 minus e raised to negative 2at dt, and now again use the substitution, u is equal to e raised to negative t. Therefore du is negative e raised to negative t dt, which gives us 2 times integral from 0 to 1. I'm just directly flipping it. I don't want to show everything. U raised to s plus a over 1 minus u raised to 2a, but we also have this other factor because dt is negative du over u. So we have this -1 here, and the negative was used to flip the order of integration. Now we can use the geometric series like before, but we don't have this alternating term luckily. Sum from k equals 0 to infinity, integral from 0 to 1, u raised to s plus a minus 1 times u raised to 2ak du. So just calculate the antiderivative we have. After evaluating, we just get 1 over s plus a plus 2ak divided by 2a, so we 1 over a, sum from k equals 0 to infinity, 1 over s over 2a plus 1/2 plus k, and now we can use the Lerch transcendent, I think. So 1 over a phi of 1, because there is no alternating part, so no -1, 1 because the power in the denominator was 1, and s over 2a plus 1/2 because that's the term associated added with the summing index k. And there we have it, the Laplace transform of the hyperbolic cosecant of AT. Now moving on to the hyperbolic tangents and hyperbolic cotangents. See you on a fresh page. Okay, so now what I've done is again expanded using the definition. We can just divide to get negative powers everywhere. There's no carry forward factor because it's a fraction this time. So 1 minus e raised to negative 2at divided by 1 plus e raised to 2at, the negative sign, dt. Now we can use u is equal to e raised to negative t again, which means negative du over u is a dt. Just have integral from 0 to 1 u raised to s 1 minus u raised to 2a divided by 1 plus u raised to negative 2a. This will be minus 1 because of this dividing u du. Again use the geometric series. Sum from k equals 0 to infinity minus 1 to the k because there's a plus over here. Integral from 0 to 1 u raised to s minus 1 1 minus u raised to 2a. We have u raised to, I think this will act as a positive power because of this substitution, my bad, 2ak du. So if we split, we have two integrals by linearity, minus 1 to the k, integral from 0 to 1 u raised to s minus 1 plus 2ak du plus minus 1 to the k, integral from 0 to 1. There'll actually be a negative here because of this. U raised to s minus 1 plus 2a plus 2ak du. And now it's just the antiderivative everywhere. Minus 1 to the k divided by s plus 2ak minus 1 to the k divided by s plus 2a times k plus 1. And that's pretty much it, because now we can use the Lerch transcendent definition. If we divide by 2a, we'll have a phi of negative 1 because now there's an alternating part everywhere. 1 s over 2a minus phi minus 1 s over 2a plus 1. Now there is one identity actually that says that phi of zs alpha minus z raised to n phi zs alpha plus n is equal to sum from k equals 0 to n minus 1 z to the k over k plus alpha to the s. So in our case z is negative 1, n is 1 because of this one over here. So phi of negative 1 rs is 1 because of the power of the denominator. Alpha is s over 2a minus, well, z was negative 1. Negative 1 to the first power is negative, so it'll make a positive. Phi of negative 1 s over 2a plus 1 is equal to, since n is 1, we have sum from k equals 0 to 0. So when you substitute in for k equals 0, you have z to the 0. So that's going to be 1. And we have alpha to the s, which is alpha, so 2a over s, which means that this guy, actually the second Lerch transcendent term, is 2a over s minus the first. And when we take a negative, because we had that originally, flip the signs like that. So finally we end up with 1 over 2a, the first term, first Lerch transcendent term. And instead of this guy, negative 2a over s, and when you add that you get twice of that. So finally we have 1 over a, Lerch transcendent minus 1 s over 2a minus 1 over s. That's the Laplace transform of the hyperbolic tangent of AT. Now let's look at the hyperbolic cotangent. So for the Coth, I'm just writing its definition and just gonna repeat the steps. So I shouldn't, bother with explaining actually, because the essential idea is the same. And in case you already might have guessed, we're gonna end up with a Lerch transcendent term again. So now we use the post substitution actually. Let me just show the steps for you. So dt is negative du over u, fine. It goes from 0 to 1. U to the s plus u to the 2a, 1 minus u to the 2a minus 1 because of that, du. So now geometric series, u raised to s minus 1 plus u to the 2a, u to the 2ak du. Split this guy up entirely into two integrals by linearity. U raised to s minus 1 plus 2ak, u raised s minus 1 plus 2a plus 2ak du. Well, the first one turns out to be 1 over s plus 2ak plus 1 over s plus 2a times k plus 1. So if we divide by again 2a, we get Lerch transcendent of phi of 1 s over 2a plus Lerch transcendent of 1 s over 2a plus 1. So what we can do is we can use the formula from before, but with the right substitutions. Phi of 1 s over 2a minus, well, z is going to be 1, so 1 raised to 1 is 1. Phi of 1 s over 2a plus 1 is equal to, for the k equals 0 case, 0 to 0 because n is 1. If 1 over is s over 2a so 2a over s I'm hoping I don't make any silly mistakes here, guys. So it means we have the second term, Lerch transcendent of 1 1 s over 2a plus 1 as Lerch transcendent of the first minus 2a over s factor. We can just substitute that in. So for the integral we have 1 over 2a Lerch transcendent of the first. For the second, there's two of these, minus 2a over s. So 1 over a, phi of 1 1 s over 2a minus 1 over s. And that's the Laplace transform of the hyperbolic cotangent of AT. And that's it, we're done. I hope you enjoyed this video, guys, and if you did, please like and subscribe to my channel and spread the word of gamma digamma in the math community. Stay tuned and peace out.